Well, disappointed that people show up late, and we're going to try to do some knuckle slapping when they get in here. But meanwhile, let's get started. The first thing I wanted to do is clean up something that we talked about 2 weeks ago, just to sort of tidy up that little part of the work. Namely, to have a good, to figure out a good algorithm for the problem. Given a set of inputs, zeros and ones, what faults does it detect? So this problem, what's the best way to do that? And I'm looking for a bottom-up method. I mean, a method that starts out with that goes through the circuit, sort of one pass through this DAG, and at the end you know which faults are detected. Does anyone want to describe their method for this?
You know the evaluation. Do you have the evaluation already, or do you not?
We just got the inputs. I've just got X's. You know, in other words, I know the. I can evaluate it as I go, but so I start out with knowing what X1 through X7 and Y1 through Y7 are in our multiplier. And then every time I go through a gate, I want to do some computation that essentially reflects that if this gate were an output, how many stuck-at faults would those inputs have detected at this output? Okay, you see the problem I'm asking. If you can take a DAG and cut it at any point and say, just consider all the gates less than or equal to k, and then those that and now for each of these gates that 1 to k, we can imagine that it's an output of the network. And if that were an output, or just choose any one of them as output, if that were an output, what stuck-at faults would be detected? So take a very simple circuit where you got just one gate. Say it's an AND gate, and suppose X and Y are 0 and 1. Okay, what stuck-at faults do we detect at this? Well, maybe I better make the circuit a little bit more interesting. Huh? So we might as well do an exclusive OR and then an OR, say. Okay, so now suppose that we just give some pattern to these X, Y, and Z, and we say what stuck-at faults would be detected. Well, first of all, in the first case, if I have X and Y, and I would detect it if, of course, I'm comparing the true value to to a stuck-at value. So we've got 3 gates, G1, G2, G3, let's say. And at G1, what's the situation?
It's stuck at 1 on X.
Okay, so since this is 0 and this is 1, we get a 0. Since this is 0 and this is 1, we get a 1 here, and here we get a 1. And so if this one is stuck at 1, if gate 1 is stuck at 1, then we would certainly detect the fault.
No. No. I'm saying
you wouldn't detect the fault.
I was talking of the level above. If you're considering.
Oh, I see.
He's saying assuming it's an output.
Yes.
Inductively.
Yes. You're right. If the output of G1 is an output.
If the output of G1 is an output, yeah.
Then you would detect the stuck at 1 on X.
Oh, I'm not considering X to be.
Yeah, right.
X is never stuck at anything.
But
yeah.
The general.
So I have a set. So there's got to be a set. Let's say S1 is going to be the set of gates, the set of stuck-at faults that would be detected by 0, 1, 1. If G1 were an output, and I'm saying that's G1 stuck at 1 would be the only one that we detect, and S2 is well, this is too easy because it has only one gate in it, so it's too trivial to be considered. But now S3 is what? Now, see, so this S3 says stuck at, okay, well, certainly G3 stuck at 0 would be one case. But what about others?
G2 is stuck at 1. Sorry. G2 is stuck at 0.
Yeah, it would have to be some subset of the input. I mean, it has to be in those two sets. It either has to be this gate itself, or it has to be one of those in the gates, in the gates before it. That occurs here. So it's got to. So what about G1 stuck at 1?
No, because
it's not present because that one gets masked by the 1 here. But G2 stuck at 0 would not be masked by that. So we pick up one of the. So we pick up one of them. Now my claim is that there's a way to compute these sets. As we just like you compute the values of a DAG, in a procedure that I call bottom up, although it seems to be going downward on the blackboard. Procedure from the inputs to the outputs. There's a top-down procedure, the converse procedure that we observed the other time. Well, no. Well, we had a theorem that said that if this final circuit, it would involve, say, G2, if and only if the value of f, G3, expressed in the terms of x's, was going to be G2 times f of times some function that's f1 of x, y, z plus f2 of x, y, z, where these are where we would expand the function. We'd expand this function down into the original values x, y, and z, except when we got to G2 we wouldn't further expand G2, and we reduce all ands and ors and exclusive ors to polynomials in plus and times. And if and only if f1 was equal to 1, was G2 a stuck at fault for this? Well, now, maybe you, since nobody answered the original question so readily, maybe you don't have the same. Maybe you have a different way of computing these things. I mean, somewhere along the line, you probably have to have in your program a solution to this problem. Maybe not.
I've been kind of concerned about one problem that comes up.
Mm-hmm.
I don't know if it's taken care of in your method or not. I was just trying to look at a little example where if you assume that you do have a stuck-at fault at one gate, and that gate has many outputs and propagates sort of apart,
Mm-hmm.
that later the combination of the faults on many lines will come back together to give the right answer. Cancel out.
So two wrongs make a right, or something like that. Yeah.
Right.
As they say. Okay. This will have to be detected in here. That sometimes you might have a case, for example, that something is that both inputs to an exclusive OR would be affected by a stuck-at fault, for example. Yeah, this should come out of our. If we get an algebraic rule for how to calculate S3 based on the two input on S1 and S2, then that should solve that problem, and it's an important problem. At least it worried me for a long time.
So the function would have something to do with which ones would...
Right, so let's take for example, for any OR gate. Suppose we have an OR gate here, and this is, the OR gate is G sub n, and it has as its inputs G sub I and G sub j. Now I want to calculate S of n. in terms of S of I and S of J. And the S's for the inputs are 0. These are empty. The empty set here, S is equal to the empty set on the top row for any of the inputs. So I can assume that these are gates with no stuck-at fault. Okay, what's the formula for this? And I'll give you a hint that there's one that I know is always in there. We can also use the values, so let's call it V sub I, V sub J, and V sub N is the value of the gate. V sub N being equal to V sub I, or there's all these V's on the board here. I have to invent a new symbol for or another word for value.
Well, certainly that gate itself would be complemented value.
Yeah. So V sub N with V sub N bar, with the opposite value of V sub N bar, that would certainly be a fault that we would detect if it were stuck at the wrong value. Okay, and then what?
And then you get,
Yeah, and now see what we did here. We somehow picked up S2 and not S1.
yeah, you get the guys in S. You get the guys in S2 because the other one is 0.
VJ times TJ.
Okay, so you have something like union VJ.
If VJ brings you J or whatever.
Yeah, okay, so you're saying it. We got
Use APL.
use APL. Right. Okay, so we have well, there's various there's all kinds of ways of notations, so I have to just choose one at random. So then we say S sub I if
Not VJ.
If not VJ. Okay, so if VJ equals 0. Right? If VJ equals 0,
S sub I minus S sub J.
And similarly for FSJ.
okay, so now we've got some competing comments on the floor here, but I got to write something down before we can argue. Now somebody said, what about just the S sub I minus SJ, the ones that are in SI and not SJ? If VJ is 0. So this is anyway, some formula like this seems to be involved, and we should be able to work out what it is. If VJ is 0, then that means that we're taking an OR of 0 with something that we had as a stuck-at fault that was recognizable here, and the value is coming through down here. So it looks as though it ought to be. It looks as though we ought to be able to detect that stuck-at fault also after G sub n. And similarly, by symmetry, this case here. But Arif, why did you say is S sub I minus S sub J?
Basically to cover the fault that Karin was talking about. Supposing the same fault is propagating down from over both sides.
So both of these are out there, yeah.
In that case...
Now you have to know what I mean by V sub J. V sub J means the correct value.
Yeah, that's right.
Without faults, yeah.
So here V sub J may be 0, but if the fault is coming down through J2, then under that fault condition V sub J would be 1.
Right.
In which case the fault would not propagate through.
If GN were an XOR, that would be right?
If GN were an XOR, then we would have a different situation than an OR.
Right.
I think so. But we'd like to have a formal. So Arif's saying is that suppose some gate, some stuck-at fault is detected in both of these places, and that VJ is 0. So that means that really the value coming through here with the fault is 1 on this side, and it's wrong on this side. So then the value that comes through on here is going to be always 1. And so he's thinking that it's not, that we're not detecting the fault.
Not necessarily detecting the fault.
We're not necessarily detecting the fault. Yeah. So in what case are we? So we're getting a 1 at Gn, and we're detecting a fault only if the true value should have been 0. Now the true value should have been 0, assuming that Bj is 0, if and only if this one was 0. Okay. But we have the wrong value on this guy, so the 1 is here, and so I think we're okay. The true value of this one then would be 0, and so I think this formula is correct.
I didn't follow that.
Yeah. Well, let's prove it algebraically by erasing it. But thank you for your courage, because maybe there was somebody else in the room that didn't follow it either. Okay, so Arif's objection was that if you had a...
Yeah, I followed his objection. I didn't
follow his objection. You didn't follow my... Oh, okay. See, I was saying it doesn't matter, because we would pick it up if the true value of G sub n is 0, because we're getting G sub n equals 1 under those hypotheses. And if the true value is 0, then we are detecting the fault. If it comes out 1.
The problem is if the true value of G sub n is 1 and it's created by one of Vi and Vj being 0 and the other being 1, because if some fault is showing up in both Gi and Gj, then it's just going to switch the 1 and the 0, and it's not going to change the output of G sub n.
Okay, so you're saying that my conclusive proof was also false. That's interesting. Okay, so you're saying that we have a case of a 0 and a 1, or let's say a 1 and a 0 inputs to the thing, and both of these are in error because they're both carrying a certain fault along in them, and it's detected. So some gate back there made a mistake, and it's been picked up by both of these. All right. Now. So you're saying that these are the true values, the actual values are going to be 0 and 1, and therefore we're coming through with a 1 at the output, and that also looks convincing. What happened to my argument? Okay, so now you're saying that then the values that we find here are 1 and 0, and we come through and take the OR, and we still get a 1.
So it seems like you're taking that set Sn and then taking the difference of the ones which are in both.
So
look at all 4 cases of Vi and Vj.
Okay, so if you got a 0 and a 1, and then somebody is in both of the sets.
That guy, because he's visible on both of the sets,
Right.
it's actually changed the values.
Yeah, so it's
So you get the exact flip,
yeah, and so it still comes out to a 1 at the bottom.
and it's not detected.
Yeah. Okay. Let's use algebra instead. What I mean is we've got some gate G, and G sub I is equal to G plus 0 or 1. When we write it as polynomials in the inputs, G sub I is expressed as, go to my previous notation, it's equal to G F1 of X of the inputs. I'll suppress the inputs, it means all the inputs here, plus F2, where we've written it as a polynomial modulo 2, and F1 is known to be 1, assumed to be 1 if G is in the set of the faults there. And F2 could be either 0 or 1. So F1 is equal to 1, but F2 is either 0 or 1. So expressed in terms of these inputs, I could say that GI is equal to G plus 0 or 1. Similarly, GJ is equal to G plus 0 or 1. Well, let's see. That's in the case that that's in both sets.
I'm a little confused as to what these small g's are representing here.
Okay. Let's, okay, I'm imagining that G is any gate less than or equal to n, or less than n. And then I write G sub n, and I want to write G sub n is equal to G times F1 of the inputs plus F2 of the inputs. Okay, and I want to imagine that I've done this algebraic calculation where G is the previous gate, and I don't expand G to its inputs, but everything else in the circuit I expand out to its inputs. So I imagine taking the network at Gn, and every time I have a gate, I replace it by its inputs, unless the gate is G, in which case I just stop dead. Eventually I get a polynomial in all the inputs. Okay, now the question is, what is F1 and F2? So I don't like this notation. Let me call it Fn and Hn, so that I've got a better notation to work with. Gi was equal to G times Fi plus Hi. Gj is G times Fj plus Hj, some assumed gate. Little g is any gate, and we can imagine that we've already computed the Fi's and Fj. So there now, what are Fn and Hn according to if we have an OR gate there? Well, that's Gfi plus Hi, or Gfj plus Hj. So we have to reduce this OR to a polynomial modulo 2. OR is the hardest case. Plus and times are easy. So the OR case is the complement of the AND of the complement. Like by P. Morgan's famous law, this next OR in there. Okay, and the complement is obtained by adding 1. So polynomially, this equal to this. So now from this I should be able to determine Fn and Hn. So we write this out. G squared is equal to G. In modulo 2, x squared is equal to x. So we have G times Fi, Fj, plus Hj plus 1 is that term. Then here we get an H. Sorry, this is an Fi Hj plus Fi.
You've got an FJ H. Oh, I'm sorry.
Okay, and the next one is Fj Hi plus Fj. Okay, and then the other terms are Hi, Hj plus 1, and so on. Hi plus 1, Hj plus 1, plus 1. So, in other words, this is Fn, and this is Hn in this case. Hn is actually the OR of the two H's. And this is something depending on the F's and the H's. It looks like if I rewrite this, I should probably know more Boolean algebra, but so I have to stick to this part of the board. So I'm going to now go up here and rewrite it. What do we get? Well, it's a coefficient of G is but then the bottom one is the complement of Hi times the complement of Hj complement. So that's H or Hi or Hj. And then what about this one? Well, the same kind of a thing seems to be here. The Fi, Fj, Fi, Fj is Fi or Fj. And then there's plus Hi, Fj plus Hj, Fi. Okay, so now let's see. What are the H's? Are the H's the same as the value of the gate? Is H... Is it true that H sub n is equal to V sub n? And Hi, is that?
Depends on G.
Does it?
If G is supposed to be 0,
See, G is any gate. Yeah. If G is a gate that's supposed to be 0, yeah. If G is a gate that's supposed to be 1, then it certainly won't be. Yeah. But I think I computed this right. Let's see. I'm trying to get at as a rule for calculating H and F and H and I think I did it right for an OR gate. So let's do it for an AND gate. So for an AND gate, I have GFI plus HI ANDed with GFJ plus HJ, and this is equal to GFI FJ plus HI FJ plus HJ FI plus HI HJ. And in the other case is GFI plus HI plus GFJ plus HJ. And this is equal to G times Fi plus FJ plus HI plus HJ. So in each case, the constant term here, the thing that doesn't depend on G, is is obtained just by using the ordinary gate rule. And so by induction, this should equal V sub I. Can I make a fundamental error here? Maybe we've proved that 0 equals 1. I've always waited. I mean, there's a lot of corollaries. What?
Mod 1 arithmetic.
Mod 1? Okay. Yeah. Okay. Well, now let me see. So I got to. Let's see. So Gn is a function of the input, and we can express it in this way. And if its true value is always equal to H sub n, then that seems to be contradictory.
No, it's not, because I mean, if your Fn happens to be 1 and the gate that's hidden way back in the works that you're detecting the fault at is supposed to be producing 1, then GFn is going to be 1, and so G sub n is going to be.
You say, yeah, if this is, if G is, if that gate is supposed to be producing a 1, and if Fn is 1, then we seem to be picking up the wrong value. So what's the there should be an easy counterexample. And sorry, I shouldn't be wasting so much time here. This is X. Suppose that I have a simple case where I've expressed G is my first gate in the system. So let's say G1 is equal to G1. Little g will be G1, and I'll just say G1 is equal to G1. Now G2 will then be that's where my induction breaks down, right there at level G. When I is the value that corresponds to this little g here, then Hi is not V sub I. Except for that, HI is going to be V sub I. Okay, so the same calculation works on the H's as works for the as for the V's, except at node G itself, where it's always 0. Okay, that's where I slipped. Okay, well, now back to where we were then. This is a rule for calculating the set, namely the values for which this is equal to 1, it will give us the set of values for the gate, and it means that the H's. So a rule like this should be derivable from this formula. So let's take a look at it closely. Maybe it simplifies down, but here's what it tells us. We want to say when is this coefficient equal to 1, and so we know the set of gates. We know. Let's see. We know what Fi and Fj are based on the S's for the inputs. Namely, Fi is 1 if and only if G is an element of Si. But we don't know the H. We don't know the H's. Well, we sort of do know the H's. Yeah. Okay. So it looks like my algebra isn't doing much better than my directly reasoning from cases. So let's get so we have to consider various cases that Fi is equal to 1. In that case, then we know that Gi is equal to G plus Hi, and the value V sub I is equal to G plus Hi. That's weird because it depends on the true value of the gate in question. This says that G is an element of S sub I. And so we want to, if Hi is, okay, if
what is S sub I in terms of the S sub I and S
sub I, yeah, S sub I is equal to the set of all G such that G sub n equals G
set of all N, you mean?
Plus H sub, yeah. See, H sub n is not is actually a function of it's a function of G. I mean, these F's and H's are specific to choice of a certain gate. For every little G fixed here, then I get a set of I get a Fj and Hj.
But the H shouldn't involve G.
The H.
This whole confusion is there's the G that represents the gate, and then there's the G that represents the output of that gate. I mean, probably need another subscript in there someplace.
Yeah, one of the main rules of technical exposition is to try to avoid subscripts when you can, but sometimes the identification of values without subscripts is worse, huh? But this adding a subscript trap is what we try to avoid. Okay, so let's see. H depends on G in the sense that that if I had another if I was expanding with respect to another gate, I would have wound up with a different remainder, h. Okay.
It's very confusing without specifying that dependence.
It's what?
It's very confusing without specifying that
Without this,
dependence.
yeah, right. So that's Fn,
say
FNG and HNG somehow are the
Why don't you say that, like, call that gate number K?
gate K. That's it. These are K, FIK, HIK. That's it. Like that. All right, and now we've got our recurrence formula. That says. I mean, these formulas, I think, are correct, and then we should maybe see that the whole thing simplifies later. Let's see, namely FNK. When we have an OR gate, FNK was equal to FIK or FJK. Plus HIK FJK plus HJK FIK. And then we had on the case end the H and K was equal to HIK or HJK. And this rule holds for if n is greater than k. So reference all this by n greater than k. If n is less than k, then f is 0. And h is, well, n is unequal to k. Anyway, we know that. If we have an AND gate, f and k was the same formula but with AND instead of OR. Exactly the same. So I don't have to write it neatly, right? H and k is h I k and with HJK. Now in the plus case, FNK was equal to FIK plus FJK, period. And HNK was equal to HIK plus HJK. So that's the case of n unequal to k. When n was equal to k, you have FKK equals 1 and HKK equals 0. And that's the way you expand the gate in terms of itself. GK equals GK. And so we have this way of calculating on an input, the case of an input, the F's are 0 and the H's are the value of the input.
Probably try expressing the S of i's in terms of that.
So S is the set of all k's for which f of ik is equal to 1. Now I changed the S a little bit. Before I had a gate in there, and I said it was a gate stuck at a certain value. Now we can always say that a gate is in there stuck at the wrong value. There's a certain value v sub k. So it's really, according to our other notation, it was a set of all g sub k vk bars. The opposite values of
Capital G.
Yeah, did I have capital G? Mm-hmm. Okay, well, I lost
capital G to represent the gate and the little g
to represent the formula for the gate. And Okay, so we have we now have the capitalistic theory of faults here. Now all we have to do is to work out a bottom-up way to calculate, see if we can simplify it. Now let's see. I thought that this was all going to be so simple, but it's sort of like if we're going to vary, like when Ramsey grades your problems, he's going to at least have to have a routine like this to see if you've really covered the faults you claim to have covered, right? So somebody has to know a way to calculate these.
Reliably.
Reliably, right? You can't just trust somebody else's claim. All right. So now let's see. There ought to be a relation between HK and VK. I guess it's obvious. Because you plug in, like V sub n will have to be equal to V sub k times Fn k Hn k. So that's so there is a formula that we can compute V n knowing Vk and Fnk and Hnk.
Well, actually, you have V sub n is equal to V sub k times Fnk. Right.
So now G sub n is either 0 or 1. So G sub n is the same as V sub n. Yeah. So we might as well just use that notation. So those are the values of the gates. Let's say G sub n now is the value of gate n, the true value of gate n, right? So this formula holds for all n, and this gives us a way of calculating the f's and g's recursively from the bottom instead of going from the top. I mean, going from the inputs to outputs instead of going from outputs to inputs. So it looks as though it's that the matter of which to throw, what case to throw in here in order to get the f's equals 1 is going to depend on knowing these. So let's expand that out and see if that simplifies. So I'm just going to go back to so G sub n was equal to G sub k times F nk plus H nk. And now I want to rewrite this formula and see if it simplifies. So Fnk is equal to Fik or Fjk plus, now here's Fjk times Hik. Well, Hik we get from that formula as Gi plus Gk Fik. This is going to work. Plus Fik, I think, times Gj plus Gk Fjk. I'm just plugging in for Hik here in this formula. Hik, I could use a minus sign, but minus and plus are the same modulo 2. So now what do we notice coming out here?
Cancel GK.
Yeah, these terms cancel with each other. So therefore, I can replace the H by a G here. Hi and Gj, and then the same thing here. So it only depends on the values, what we used to call G sub I, G sub J. It only depends on the values, the V's that we had before. And so that gives us a rule then to get in an OR gate situation. It says that you have the union of the two previous sets, except you take out the sets that are in Sk if Gj is 1, and you put back and you take out this the sets of Si if Gj is 1, and take out really means complement the status of. So you can compute then based on the values of I and j and the previous sets. You can compute which of the things go in and which go out. So it's a sort of a Venn diagram situation. You have Si here, and Sj here, and Si is the cases where the Fik is 1. And so if you consider the case of Si, Sj. So we got elements that aren't in either Si or Sj. Elements outside. For that, both F's are 0, and this whole term is 0.
Okay.
We have the case where the element is in Si and it's not in Sj. If it's recognized by the I input and not the j input, that means that Fi is 1 and Fj is 0. So we get a 1 here, and I get a 0 here, and I get Gj there. And so the thing is in so we use Si minus Sj if the elements of Si minus Sj if V or V sub or G, I guess we might as well say, if G sub J is 0, and Sj minus Si if G sub I equals 0, and Si intersect Sj, the things that are common to both, those have F, all F's are equal to 1. So we get 1 here plus Gi plus Gj, and this is if Gi plus Gj is equal to 0. So either they're both. So in the case, so the interesting thing then about an OR gate is that if there's a stuck-at fault that appears on both of the inputs to the OR gate, that stuck-at fault gets through only if the values on the two legs of the OR gate are unequal. You know, the 1, 1 or 0, 1. I'm sorry, equal. Yeah. If you have a 1, 1 or a 0, 1 coming through an OR gate, then you pick up the stuck-at fault out the bottom of the OR gate. But if you have a 0, 1 and a 1 or a 1, 0, you don't. That's the solution to how to merge them in the case of ORs. And the case of ANDs will be similar, except that I think we omit the first two cases here. And the case of exclusive OR is easy because you just take the exclusive OR of the two sets. Okay, well, long algebra, long time. Let's unless we have a question on this, it'll all be clear when you read the notes. In case it isn't clear, immediately clear now. Read.
Essentially, what this means is simply that you divide the inputs into those which will give you 1, those which will give you 0, and if the complements of the inputs are on the opposite side of the camp, then the fault will get through. Given that it's coming in on both sides. If it's on the same side, it won't get through.
Yeah, maybe that would have saved us 30 minutes to have seen that. I don't know. I always am reassured by algebra, although there's a difference between me and other people, and sometimes I like to do something in a different mode where I don't understand what I'm doing except algebra, and then it still gives me something that I can interpret in the real world, gives me some confidence. Okay, now the other thing on my agenda for today was to talk about covering problems, and now that the covering problem for the half-rad circuit is presented in this little chart, And the one in the circuit that we have really for the problem is a little different, because in the real problem we have 65,536 rows and 802 columns. Now in the real problem, we observed on Tuesday that one of the columns has no x's in it. The x means that this input will detect this fault, and one of the columns had no x's in it at all, so there was no way to detect that particular fault. And then we observed that that didn't matter as far as being able to multiply everything correctly. Now the general, then you could find an optimum solution if we had a nice subroutine that you could call, would take any matrix like this and find the smallest number of rows, so that the union of the rows contains an x in every column, that there's an x anywhere. So eliminating the column that had no x's in it at all, then you get a situation like that. Now I've chosen this smaller matrix just to indicate. Let's see if we can't find, at least for the half adder, the optimum solution, the very best way to cover all the faults. And then just think about some things that generalize. Okay, so what's the first thing that would occur to you if you were faced with this problem? You know, it's a prize contest in Games Magazine or something like this. Kathy, what do you think?
I guess the best way to start doing it is to if you count across, you can count across the rows and see how many faults are detected by each. 5, 5, 5, 5, 5, 5, 5, 4, 5, 4, 4, 4. Okay, so the ones that, so you try putting in the one that detects the most, and then. Okay.
This is known as a greedy approach.
Yeah, right.
We're trying to cover 10 things, and we might as well choose one at the beginning that covers 5. Well, then we're half done. Something, right? Okay. Okay.
And then you go on. Then you don't consider the rows you've covered now, and you choose the next element using the same.
Okay. So suppose we choose this one, which covers 5. Then we have 5 others to cover, which are easy to characterize because they're all the left.
All the ones we only consider the ones we haven't covered.
Yeah, this one gets all the stuck at once, and so and so now the other cases then it gives us a reduced matrix with five columns in it, and it looks like this, huh? I hope I did this right. We're taking the five remaining columns, and I think we get a pattern something like that. So if we chose this one as our first run, then we have 5 columns remaining to be covered, and this is 1, 2, 3, 4, 5, 6, 7. So these are the. What did I do?
You've got an X at the bottom of the 4th column.
An X at the
bottom of the 4th column in the new table.
You're missing an X.
This one.
No.
1, 2.
The 4th.
No, the new table. Okay, so this guy's got to go in here. 1, 2, 3. Here. Yeah. Okay. All right. So we can't pick up the remaining 5 with another swoop like that.
Next, I would check the column to see if there is anyone with only one.
Okay, so there's a row method and a column. Yeah, so you check the column to see if there's anything there's only one way to cover it, and it's not so. There aren't any unique ways to cover it. But that's another thing that you can say, that every column has to be covered somehow. If there's only one way to do it, then we might as well force it in there.
Well, you might as well take all those right at the beginning.
You could have done that at the beginning instead of. Yeah, you can all, yeah, right. At every step, try to look for forced moves, because that will certainly eliminate backtracking or other things to try. Okay, so now, but we have cases where there's only two.
That can
Like, look at this column here. This column here, we've got to choose either 101 or 011.
Come up with a big long Boolean expression.
You write a big long Boolean expression and just plug it through find the minimum term. The min term, yeah. That would do it too. I mean, it's we've now shown it's a solvable problem.
I got my non-deterministic Turing machine in there.
That's right. There's that's the proof that it can actually be done not only in that we can actually give an upper bound for how long it would take to find that. It would be polynomial in the exponent. Yes. Okay. This is there's something now staring in the face though about this that I'm waiting for somebody to say. What about?
Oh well, you never take an input if another input subsumes it.
Subsumed? Well, that's even more general than I was even expecting. Thank you. We went 2 steps. Subsumes means what?
It includes everything the other one doesn't.
Okay, yeah. So are there any rows that dominate another or subsume other rows? Because if something covers everything another row does, then there's no reason ever using the other row. What?
Well, 011, 101 are the same.
Yeah, these are equal, and so we can pick one and throw away the other. Right? And in general, if you had a subset relation between any two rows, you could take away the smaller of the two.
Well, the thing is, the greedy algorithm will do that automatically.
The greedy algorithm does that automatically, but
this way you just force.
This way we find a forced. This way we find a forced move, which we didn't find otherwise. Yeah. So this tells us that without loss of generality, we can put 011 into the set. Now the greedy algorithm wouldn't have picked that because it's the only one left that has only 4 in it. It's the one that the greedy algorithm wouldn't have picked, but we know that sooner or later we'd have to pick it anyway. So we do get a reduced. I won't bother recopying it. I always make a mistake. I'll put, but this can be done with all lots of generality. So we've already covered this fault and this fault.
Well, you're right. 010 and 100 also have the same.
Okay. Which one?
010 and 100.
010 and 100. What? This one?
Yeah, that's true.
Okay. So these were even true in the beginning, and after you cross out columns, some things, more dominance or subsumption might occur. So let's cross out this guy too. Okay.